Thanks for the introduction. So yeah, I have a cool job. I'm the cooling guy. And part of that is around keeping electronics cool, but it kind of extends a lot further than that. I'm involved in EuroEXA, where not only am I doing the cooling, but looking at power distribution, infrastructure, the data center, and pretty much everything down to the PCBs. But I also do the dissemination exploitation for the project. So today I'm going to tell you a bit more about EuroEXA. So the route to Exascale kind of takes us on this journey where in the European Union there were 14 initial projects with a relatively narrow focus, looking at particular technology areas. And they were invested in around 2014, 2015, and then narrowed down to two what they call co-design projects, where they start to bring these different separate projects which were focused together to complement each other. EuroEXA is one of those co-design projects. Following on from this, we expect what's called European Exascale demonstrators to occur. And there'll be a number of those over the next few years to demonstrate how we could do exascalable supercomputers. We hope actually within EuroEXA to be able to demonstrate something relating to exascalability as part of our objective. And then we have the first Exascale machines to be turned on in the EU somewhere between about 2021 and about 2024. And they're buying two. So I put this slide up in case people don't know what Exascale means. It means a different thing to a lot of different people, actually. To some people, it's all about flops and top 500. To a lot of people in Europe, it's actually more about application. And I think that's generally the mindset of the European Union, is this is not a vanity project. This is about investing in European supply chain, applications, real science, and real-world investment. They're looking to maximize return on investment for the economy here in Europe. Whereas, abroad, I think there is, in some territories, a vanity project going on. And for some places, it is about flops. So I put down here a billion flops, or equivalent, as Exascale. The expectation is between 20 and 60 megawatts of IT power, which is a lot. Recent US call that went out put it at 40 megawatt cap for their RFPs. So sometime in the EU between 2022 and 2024, we'll have these things switched on. In the meantime, pre-Exascale machines and Exascale demonstrators. And they already have €1 billion to start buying these. Now, there are a lot of big challenges for Exascale. Being the cooling guy, there's one area I'm going to focus on today, which you might find interesting. We've got things like programming models. How do you scale applications? How do you make things resilient? How do you actually have a supply chain in the EU where we don't have a lot of substantial supercomputer vendors? It's a big issue for us. Scalability of not only software, but also reliability, hardware, resilience, infrastructure. Large issues there. Now, this is an interesting one that I'm going to look at today. Latency, cooling, density and distance, and energy effectiveness. Everybody in the room's heard of Moore's law, right? It's not a law, it's a trend. I don't know why we call it a law. Who here has heard of Kumi's law? Can I have a show of hands for Kumi's law? Who hasn't heard of Kumi's law then? Okay. Kumi's law is like Moore's law's brother. It says every 18 months, microprocessors double in energy efficiency. Right? Moore's law was about doubling the number of transistors and the computing power. Kumi's law is about doubling the energy efficiency. And it shows a trend since the beginning of time for the people in the industry in the room of doubling in energy efficiency, which, as you can imagine, is very, very closely tied to Moore's law. One of the things is that these guys have bumped into a real law of physics. Shannon Hartley. And that's about the amount of energy it takes to transmit a bit of data over conductive means. It's all associated with the smallest amount of available energy in the universe. And this graph nicely illustrates how these trends have hit Shannon's law. We got on the horizontal axis here is distance, and on the vertical axis we got logarithmic energy. So this is our double precision flop that's processed, a number of picojoules per 64-bit operation up here. The blue line is 2008, and the red line is 2018. And what we have, quite expectedly, a 10x improvement here in processing energy consumption in 10 years. Great. And moving around the silicon, because the silicon's got denser, Moore's law, we've got a nice improvement again in energy efficiency. We start looking to move in physical dimensions. We've had no change in 10 years. That's because we've hit that real law of physics. And then when it comes to optical transmits, which are over here, they tend to break even at the moment about 50 centimeters. We've got a general improvement going on, but it's still orders of magnitude away from the copper. So break even about 50 centimeters right now. So looking at this, well, how are we getting the energy efficiency out of the systems in the last 10 years? Well, if you notice how the RAMs move closer to the processor, in many cases even onto the package. They call it high bandwidth memory. You see it on Knight's Landing. Yeah? What do you think the Knight was landing onto? The package, right? And we find these things getting closer together. If you think back 10 years, we hadn't got those nice twin half-width boards. The movement towards those was actually about moving the memory closer to the chips, the two chips closer together. If you imagine previously, you had the chips quite a long distance from each other, and the distance from the chips to the RAM was quite substantial. And then we ended up kind of aligning the processors, which thermally was very suboptimal, and splitting the RAM on either side of the processors to reduce the transit distance. And that's how we're pulling this off, because this makes a density problem for scaling out. Density and energy efficiency is becoming a problem here. So looking at a co-design project, we can manage to make things denser and closer together. We get energy efficiency savings. We also get latency savings. And those latency savings and those energy efficiency savings all come together to reduce our IT power and reduce our hardware outlay in achieving our application performance, which is what we really care about in the EU. So we're likely to have a very, very dense exascale supercomputer rather than one that's spread over a square kilometer across a mountainside. So EuroEXA had 3 feed-in projects from the previous focus projects, and then it had a donation of intellectual property up here, and a substantial amount of EU funding here. The total value of everything on this slide is around 100 million euro of NRE investment in getting to exascale. The objective, a 4x improvement into performance and a 4x improvement in energy efficiency overall, holistically, across all areas. And these were the people that were selected as a result of that competitive exercise organized by the EU. A number of SMEs and large commercial organizations here, some academic partners. I'm sure many people in the room will recognize these guys, and then supporters, including Square Kilometre Array, Xilinx, Schneider, Solvay. So some big names there. And co-design is this gift that keeps on giving. We make improvements in applications, we get improvements in storage network and architecture, we get denser and more improved electronics, we get better cooling, and we just keep going around this. We find that making one change somewhere often has a knock-on effect somewhere else in a positive way. And then that knock-on effect then has a knock-on effect somewhere else in a positive way. And we found ourselves just keep going around this cycle. Oh, because we've done that differently over there, we're able to improve this over here. Whereas before, we all sat in our silos. The number of times I've heard someone say, oh, that's a software problem, or that's a hardware problem, or that's a networking problem, or a cooling problem, making it someone else's problem. But in a co-design project, making it someone else's problem is not allowed. Yeah? It's all about working together to reduce waste within those areas of interaction. As part of the project, we're producing 3 substantial test beds. First test bed that's going in around now, and I've got some pictures of it actually. A second test bed that's going in early next year, about a year's time. And a third test bed that's going in around 2020. So the idea is the one that goes in, that's just going in now, this one is based upon existing infrastructure tech, but new node tech to enable software testing. And then the next one comes along, that's new infrastructure, existing node, and all the learning that's come from the software goes onto that. And then the last one is an update to everything. A little bit about the architecture. We're looking at ARM processors with reprogrammable FPGA accelerators attached to them to make a fully reprogrammable accelerated computer system. Partition global address spaces, memory compression technologies, distributed storage and distributed memory across the whole system, and a unique hybrid geographically addressed switching and topology interconnect. The idea is to minimize the data transit over the system, but still make a globally available storage and address space by distributing the memory and distributing the storage. In terms of the applications, we have a mix of applications from across climate, weather, physics, energy, life sciences, and bioinformatics. And without going into too much detail on those, I've listed the organizations here. And if anybody has a particular interest, I'll connect you to them. So, the first test bed. This is a cabinet of the first test bed. For those of you who may have come across Iceotope liquid cooling technology previously, this is an existing Iceotope system which was first installed in 2012 of this style of technology. And we've used this to house nodes so that the software can be tested upon it. But in order to achieve our targets, we need to improve density by 4x. That's a substantial improvement. Well, that starts at electronics, because you can't go and squeeze 4x density of today's electronics into a system. You're going to damage your benefit, because things will still be spread out on the circuit boards, and you're not going to be able to physically pack them in tight enough. So we have to look at redesigning the electronics for density. We've got 4 of these processors and accelerators on a daughter board. Now, this daughter board is about the size of a coaster or a beer mat. So something that big with 4 boards on it. And then hanging off the underside, we have M.2 SSDs and RAM modules, just dangling off the underside on holders, and a daughter board connector that plugs into a carrier board. This is what the carrier board looks like. So we've got 16 slots. On the underside of the carrier board, in the center, a high-speed network switch. And that fits into a 1 OU tray. We used Open Compute U's instead of standard U's because it gives us an additional 2 inches of width, which normally is wasted inside of a cabinet. And then coming out the front, you'll notice these connectors are pointing sideways. There's a reason for that. If we make them point forwards, then the cabinet has to be deeper for the bend radius of the cables. So by simply rotating them through 90 degrees, we were able to make it so that there was no bend radius of cables. They come out sideways, they bend in this space here, and we're able to reduce the cabinet depth by 4 centimeters, maybe even more. We've got 48-volt distribution, which I'm going to tell you a little bit more about in a minute. But that unit there, in short depth, is about 3.2 kilowatts. That's it packed with compute nodes as a visualization. Now, I'm going to do more than just a visualization. I'm going to show you one of these running. But because the compute nodes aren't yet finished, at 200, 250 watts each, we have to make load banks instead. So compute node sized devices with heaters on. We can get compute nodes today of about 100, 150 watts, but that doesn't allow us to test it to its limits. So we made one with an array of load banks to cycle around coolant and test our capability of delivering the power and removing the heat. This is immersion without submersion. Think about that for a second. Every component is in touch with a coolant. Every component's in contact with a coolant, but they are not immersed. They are not submerged in the coolant. So let's roll the video. So we've got these jets of coolant coming out through these heat sinks that are designed like bathtubs, and they fill up, and then the coolant overflows and is modeled to overflow over these electronic items on the edge. So it comes out and through all these fins here. So you can see the coolant level is low. Actually, the natural level sits below the circuit board. And what we have is a modeled flow over all these components, as well as through these jets. Each one of those being a compute node. The coolant is a liquid fluorinated plastic. It's a fluorinated plastic that's liquid at room temperature. So think of it a bit like Teflon, except it's liquid at room temperature. And by reducing the volume of coolant and having a very good ratio of coolant to watts cooled, we were able to make it so that we could use a very exotic coolant cost effectively. Whereas a lot of people are using like mineral oils and things like this, very, very suboptimal in terms of conditions. By reducing the volume of coolant, you notice we've got some heat exchangers at the back. That's because the coolant stays only in a single server tray and goes through the heat exchangers and then comes out the rear to be dumped. But that's a secondary coolant, which is a standard water glycol mix. There was like a tray, and there's like little sumps in the bottom of the tray. The coolant's sucked into the sumps, through pumps, through heat exchangers, out onto the processors, where it then falls off back into the tray, back into the sump, and just does that loop. And then a second coolant, which is water glycol, goes through the heat exchangers, takes the heat away. So that's the cooling system. And I'll go into a few more questions in a minute if we've got time. But power was another thing that we were really interested in. In the old way of doing things, we'd have AC coming in, we convert it to 48 volts to run batteries, then we'd invert it back to AC, and then we'd convert it to 12 volts in the server, and then we'd convert it ultimately to 1 volt for the point of load. Wow, that was wasteful. Why did we do that? Silos, once again, because, hey, that's the facility guy's responsibility, and that's the IT guy's responsibility there, you know, or the hardware guy. So we're like, well, okay, let's crush this. AC coming in, straight to 48 volts, straight to the point of load converter. And the battery feeds in here. Why a battery? Well, because we need to keep these things during the power cut. We need to keep the power clean. So lithium-ion titanate batteries, I'll tell you a little bit more about that. But effectively what we've got is a liquid-cooled 3-phase power supplies plug into a cabinet like this, 3 bars down the back, taking 48 volt DC. So we got 400 AC coming in the front, liquid-cooled rectifier, 48 coming out the back. That 48 then gets distributed up and down the cabinet into the back of the servers. and directly to that point of load converter. How many people in the room are pretty au fait with electronics or electrical engineering? Well, did you know that if you double the voltage, you quarter your electrical losses for transmission of energy? So by going from 12 volts to 48 volts, the electrical losses are reduced by a 16th for that transit distance. So by taking the 48 from the power supply all the way into the daughter board and electronics, that reduced the electrical losses, which we normally would just ignore. We wouldn't see it. It's quite substantial for 12 volts going across a motherboard. That also reduces the amount of copper that we have to use in those circuit boards. It reduces the cost of the IT, makes the boards easier to procure, reduces the layer count in the circuit boards, makes us so that we can then put denser electronics on those circuit boards without the layer count exceeding the manufacturable layer count. And all these things, co-design. Sorry? What, 48 volt DC? No. Actually, it's not even legislated in the European Union. It's exempt from the legislation because it's not dangerous. So, batteries. Now, when it comes to batteries normally, if you've got a UPS, it's holding you up for at least 10 minutes. Even if you didn't design it to hold you up for 10 minutes, guess what? It's holding you up for 10 minutes. That's because it was designed around the battery chemistry that could discharge and can't discharge faster than 10 minutes. But a generator warms up in 5 to 15 seconds. So if your site's invested in generators to keep everything running, keep all the data fresh and working, right? Then you've just gone and wasted a whole load of money on a whole load of batteries you didn't need to run your thing for 10 minutes. Well, saved by a new technology, lithium-ion titanate batteries allow you to discharge 8 times as fast. So instead of 10 minutes, we're between 1 and 2 minutes. That's more than enough time for the generator to get started, warm up, and start dumping power into the system, keep everything going in a power cut event. So we've gone and looked at lithium-ion titanate technology, which is being deployed into the cabinet attached to that bus bar. No conversion. It'll trickle charge one way, and it will fast discharge the other. It sounds simple, it sounds logical, doesn't it? But because all those silos, you know, the cabinet used to be the IT hardware guy's responsibility, and the building with the UPS, well, that used to be the facility guy's responsibility. We break the silos, we find new savings, new efficiencies to be had. So now trying to pack all of this in, we've got to start thinking 3-dimensionally. It's no good for us to think one or 2-dimensionally and think about laying things out on a single floor, because what we want to try and do is reduce the distance from one side of the system to the other, minimize that distance. We minimize that distance, we minimize the distance of transit of the data, that reduces the energy consumption in the chips, and we also reduce the latency, which improves the efficiency of the applications running across it. So we set ourselves the target around 35 to 40 meters from one side of the 60 megawatt supercomputer to the other. This means we're looking to stack up vertically as well as 2-dimensionally horizontally. And one of the easiest ways to do that was to look at shipping containers. So instead of making the servers full depth, where we put that in a shipping container, no one can get around the front or the back of it, we reduce the depth of the server so that they can be lined along the walls of a shipping container, creating a single aisle down the middle, and made it so that all the user serviceable items came out the front. And that looks like this. So in this 20-foot container, okay, we haven't got some accessories in there like electrical distribution, but just packing out with cabinets, 1.8 megawatts. So stretching that to a 40-foot container, it's more realistic that we can get more than 2 megawatts in each one of those in terms of IT. And then we can stack them on top of each other. So here's a few visualizations of what this can kind of look like. And in some cases, we could even start putting some coolers on the top. Although we'd likely have to keep the coolers separately in a ring around the stack up of containers. Because the coolers, they don't really care how close they are to the servers. We need to keep the servers close together. Who's seen this before? This is Google's barge. Yeah? You remember? It's made of about 30 shipping containers. And the distance from there to about there, from there to about there, which is one container sideways in the middle, one long ways there, one long ways there, that bit there, and that way, that thing there, that's about the size of our exascalable supercomputer. Keeping everything in those distances and packing everything in tight. And kind of another illustration, this is a data center schematic, never built, in Lagos, Nigeria, but one of these sheds is a similar size. But these were made of stack-ups of shipping containers with then an access gantry and the coolers around the edge. So you can kind of see how our exascale supercomputer can be formed out of a stack-up of shipping containers now. Our overall vision here, we want to show that we can go for a compute-centric, delivering real applications of 250 petaflops per megawatt by 2019. That's what we're going to show with our demonstrators. And ultimately, out the back of that, a report that shows exascalability could be built in 2020 with 30 shipping containers, less than 40 meters, and less than 60 megawatts. And we think we're well on the path to getting there, but only through co-design and breaking down those silos and making sure anybody that says that's a software problem, that's a hardware problem, that's an application problem, that's a virtualizer, is shot. We fix our problems together. Thank you very much, and I now have a few minutes of questions. Normally I've got a German guy standing here who then goes, don't talk about Zavor. ECMWF isn't even European. It's an international organization. But a very, very good observation. What's the impact of Brexit? At this time, Brexit has no impact whatsoever on our project. Brexit will not have an impact until it actually happens and at the end of the transition period. Up until that point, everything will be governed under H2020 rules, and British organisations will continue to be part of H2020 rules. And it's all H2020 rules that govern all the way to exascale deployment and procurement of such. Now, most of the British organisations on there that are commercial entities also have offices in Ireland or France or somewhere else in the EU as a contingency measure. But if you consider that H2020 rules also include countries outside of the EU that are fully paid up members, like Israel, for example, you may consider that Brexit may have no impact on this whatsoever. May. On the other hand, it could be a complete disaster, in which case a lot of the entities involved will execute their contingency plans. In terms of my organisation that I work for, Iceotope, we're partly owned by two large European multinationals. One is headquartered in Paris and the other one that's headquartered in Brussels. We consider ourselves a European company, and we expect to continue to operate as part of this in any scenario. But thanks for the question. Any more questions? There's got to be some difficult ones here somewhere. Don't be shy. All right. So the fluid was developed for Iceotope as a special blend by Solvay. Solvay are headquartered in Brussels and are one of the aforementioned European multinationals. Yes, by Solvay. Now, that's not to say that we can continue to use that fluid indefinitely. We could use other fluids. Solvay are certainly looking to develop new ones as well. But the important innovation here is about reducing the volume of that primary fluid and getting that ratio of primary fluid to heat, or primary fluid to IT. So you've got loads of IT, loads of heat, small amount of fluid. So you can actually use exotically engineered materials rather than having to rely on baby oil. Yeah. So it's kind of like the great-grandson of fluorinate, I suppose. Fluorinate was a fluorinated solvent, and chemically is quite different, and they submerged, but it was very expensive to submerge, and they ended up there out of necessity, but each gallon of fluorinate was about $500 at the time. You know, it would be much better if they were to have used some of the technologies that we've adapted to reduce the volume of fluorinate in the same system. A lot less volatile than fluorinate, actually. So the boxes are kept sealed with they kind of got controlled breathing on them. In a service event, you just pop the lid, put your hand in, pull a node out, shake it off. The stuff's certified for use around food production. Okay, you're probably wearing gloves and things anyway, but it's safe as safe gets. And over the lifetime, we're looking at a few grams of fluid loss each year. It's quite low. From volatility. But if you did spill a load on the floor, you'd only take out one server blade. If you say pierce the tray somehow, or you know your primary coolant's on the floor, you'd only lose one single tray because the failure domain's small, and it would evaporate about a bit quicker than water off the floor and effectively clean itself up faster than you could mop it. So also, while it's there, it's not really going to do any harm to any of the other electronics. So it's quite a safe approach. Yeah.
How does the project envisage using the FPGAs?
The project envisages using them effectively as the bulk of the computing effort. They're supported by ARM processors, but the idea is that the applications that are doing the bulk of the computing effort are running on the FPGAs, and that when you switch applications, you could optionally reprogram the FPGA to optimize to the new application. So the FPGAs effectively become the accelerator, the thing that's doing the bulk of the work, whereas the processors are there to boot the OS and support the FPGAs rather than the processors doing the bulk of the work. Cool. Excellent. Thank you very much for your questions and your attention today. I think we've probably got some organizational announcements about lunch, or are we just going? Lunch is served. Thank you.